Alright, welcome back. In this video, we're going to go over the last part of the Krebs cycle or citric acid cycle. I know I said this often, but thank you again so much for the support. 1,000 subscribers in 72 hours. That's crazy. If you find this video helpful, please like, subscribe, and comment. Comment. Talk to me. I'm lonely. It doesn't have to be about the video. You can tell me what you ate for breakfast or how your day is going. Anything. But yeah, please, that'd be great. Thank you again. You guys are amazing. Step 7. At the end of step 6, we ended with succinate. So step 7 is going to begin with succinate. Here's what's going to happen. We're going to do a little theft. All right. So this enzymatic FAD, it wants some protons to hold on to. So succinate dehydrogenases, the enzyme, is going to help commit a little crime. It's going to basically help steal the protons from succinate and transfer it over to enzymatic FADH2. Enzymatic FAD is a cofactor. All right, it's an enzymatic cofactor. Now, what's going to happen is what we just did is we did an energy deposit. Cha-ching! We just basically banked some energy for later use. That later use being the electron transport chain. So we just basically banked energy. Now, what this does is creates fumarate. Fumarate is a double bonded carbon-carbon. So that's what we did. We eliminated the protons, moved it over to enzymatic FAD to make enzymatic FADH2, and created a double bond. That's all we did. Now, this going from succinate to fumarate is an oxidation reaction. Oxidation means we lose protons. But FAD is reduced. This is a reducing reaction from enzymatic FAD to enzymatic FADH2. Because we gained protons. That's what reducing is. That is step 7. Ah, fuck. We have a problem now. This is a very common theme in biochemistry. You probably noticed this. That there's always some kind of problem. Every single pathway we've done so far, there's always something that goes wrong. This is the time something goes wrong. Here's the problem. Enzymatic FADH2 is in the mitochondrial membrane. But we need a lipid-soluble electron carrier because what will happen later is that we need to get past the membrane. This is when ubiquinone comes into play, or Q. If you're not watched my ubiquinone video, please watch that. That will be very helpful, especially if you never heard of this before. This is going to make no sense to you. Well, you can probably follow along, but, please watch it. Help me out. More watch time. So step 8. We had that enzymatic FADH2 we just made. Here's what's going to happen. No enzyme required. It's enzyme free. First time, I know, right? We're going to have ubiquinone come on and pick up the protons from FADH2. So now we have just reduced ubiquinone to ubiquinol. This is ubiquinol. This is ubiquinone. So we just reduced it to ubiquinol. This helps us regenerate enzymatic FAD. This will go back to step 7, right, what we just used. This will go to the electron transport chain for later use. Amazing, right? Easy. Step 9. Here, pretty simple. We have the fumarate we created in step 7. We're going to use the enzyme fumarase and add water. This will help us break the double bond that we formed, and create an OH group on carbon 2 and a hydrogen on carbon 3. So the double bond goes bye-bye. That's it. And this creates malate. This is a T, by the way. Sorry. My ugly handwriting. Oh, I just made it worse. Okay. Malate. Step 10. The end. So, what's going to happen here? Well, what we just did is, by the way, the reason this looks different, it's the same thing, right? CH2, this is CH2. I just wrote it differently, so it's easier for you to understand. But the hydrogen, the proton on carbon 2 and from carbon 2 on the OH is going to help us reduce NAD plus to NADH plus H. So both protons on carbon 2, right? So this is carbon 2, so proton here, leave to reduce NAD plus to NADH plus H. Okay? So this holds a lot of energy. Okay? A lot of energy, plus 23.7 kilojoules per mole. This would normally not happen because this costs energy to run. So doing this, moving the protons to NAD plus costs energy. And this uses the enzyme malate dehydrogenase. So this is unfavorable, right? So this would not want to happen. But what happens is that what we create is oxaloacetate. And this would actually go to step 1. So this is a cycle. This is called the citric acid cycle. It's a cycle. We just went on a whole circle. So let me go back to the very beginning here. I think of a diagram I put. Here, actually it's my thumbnail. We are right here, right? Malate to oxaloacetate. And oxaloacetate will become citrate in step 1. Right? So what we just did is we just went in an entire circle. And doing so, this going from oxaloacetate to the citrate is negative in energy, negative 31.5 kilojoules per mole. This helps us drive the reaction forward. So this has enough force from going to step 1 to drive this entire reaction. Does that kind of make sense? Hopefully that does. So the following reaction becoming step 1 would drive this entire reaction forward, and that's why this happens. It pulls it forward. Think about like a tug of war. One side is stronger, so this side is stronger than this side, and this helps it pull it forward. So you're probably wondering what was the entire purpose of this? Why did we just go in an entire circle just to get back to oxaloacetate and going to citrate? Well, what we did is the whole point of this is making these, right, holding energy of protons. Because remember, we're trying to deposit energy for later use, and that's what this is right here, right? NADH plus H, the ubiquinol will be created here, and then all the other steps, right? That's the purpose of it. That is the citric acid cycle. Hopefully this video was helpful. If not, then then go see someone else. But I try to make it as easy as possible, and that's my goal, right? To create free learning that's easy to learn, that's easy to follow along, so you can get A's. If you found this video helpful, once again, please like, subscribe, and comment. Tell me how things are going. Until next time, later.